Okay, welcome to part 4 of Fractal Market Analysis. Last time we talked about power laws and why self-similar objects are described by power laws. We looked at an example of a fractal, so we looked at the Sierpinski triangle, and we ended off talking about fractal dimension and how to calculate fractal dimension and box counting. So in this part, we will be looking at the logistic map, and then we'll look at chaos, and then we'll look at fractal time series. So now we'll discuss an example that I kind of hyped up for a little while, especially in part 2, is the logistic map. So that's what this is. This is the bifurcation diagram of something called the logistic map. It's a model for population growth, and this is the formula here. So this is a recursive formula. And when we talked about self-similarity, we said that quasi-self-similar, so these are objects that are not exactly self-similar, but they're quite self-similar, are usually described by recursion relations, and that's what this is. So if we think of this index, the next value of x in the sequence is described by this relation. So when we do define a recursion relation, we need a couple of initial values, and then the values after those initial values are described by this. So we'll have an x0 and an x1, and then our x2 will be described by this, this equation here. So this r is called our parameter, and our r is the growth rate. So r is the parameter we want to look at. And so what happens with the logistic map is that there are certain values of r where the system shows chaotic behavior, and then there's certain values of r where it's in complete equilibrium, and so on and so on. But the point of the equation is that we want it to capture roughly the idea of reproduction and starvation. So the population level at any given time, n, where the time is represented by n, is a function of the growth rate parameter r and the previous time step's population level. It is constructed so that when r is too low, between 0 and 1 in this case, the result is starvation. So when it's between 0 and 1, the population will eventually die, independent of the initial population. And that's kind of what I explained before. As we vary the value of r, which is the growth rate, we obtain this bifurcation map, which is right here. The bifurcation parameter r is shown on the horizontal axis of the plot. So that's this axis, and you can't see it on the slide because it's much prettier without it. But what I'm doing now is I'm just explaining how the system works. It's kind of a detail that's irrelevant once we actually understand why I'm bringing this up as an example. But for me, it was important to understand how the logistic map works in order to understand, its relation to fractals and chaos and stuff. So the bifurcation parameter r is shown on the horizontal axis of the plot, and the vertical axis shows the set of values of the logistic function visited asymptotically from almost all initial conditions. So basically, it gives you a bunch of different r values here on the horizontal axis, and then on the vertical axis, you basically repeat this recursion relation over and over and over again for different values of r, and you eventually kind of figure out where the function settles in general. So these lines here actually. So each vertical slice depicts the population values that the logistic map settles toward for that parameter value. In other words, the vertical slice above each growth rate is that growth rate's attractor. So if you have your growth rate here, the value for r here, we can see that values for the function in general, values for this recursion relation here, in general, settle between these two values right here. And then if you go over here, it settles between 4 values. So this is what's called a 4-point attractor, because it settles between 4 values, and this is a 2-point attractor, and this is a 1-point attractor. So each vertical slice kind of shows the attracted values. At R, approximately 3.56995 is the onset of chaos. So that's kind of like around this area here, and you can kind of see it's very chaotic here. And then the chaos stops here, and here we have a 3-point attractor. So right up here is 1 point, 2, and then down here is 3. I don't think you can see it. So this region here is chaos, and this region here is just another 3-point attractor, and then it goes to chaos again. From almost all initial conditions, we no longer see oscillations of finite period. That means we no longer see things like this where the values oscillate between, the values that the function takes no longer oscillate between these two. It's just all over the fucking place, right? So slight variations in the initial population yield dramatically different results over time, a prime characteristic of chaos. To me, this shows clearly the connection between fractals and chaos, and I'll show you. So right around here is the onset of chaos, right? And that happens after a bunch of oscillations between two values, the 2-point attractor, the 4-point attractor, and then it's chaos, it's everywhere. And if you change the initial condition slightly, you'll get completely different values for the function. But when we zoom in, I'll show you with this video, when we zoom in on the logistic map, it's self-similar. So there's the exact same thing right there. And this happens in the chaotic regions of the logistic map. It doesn't happen anywhere else, so. Pretty crazy. You can do this an infinite amount of times and you're always going to get this self-similarity here. So I actually wanted to revisit the logistic map for just a second before I go on to chaos. I'm filming this at a different point in time, after I've edited this whole portion of the video, and I noticed that I didn't really explain how this worked so well. So on the horizontal axis, you have your R values, your parameter values, and then you're looking at the vertical slices directly above the R values. And then on this axis is kind of, this shows sort of the general values that the function is attracted to for almost all initial conditions. So remember when I was describing about recursion relations, and let me just change my positioning here. I'll put me down here. So when I was talking about recursion relations, this is defined for like the next x. This is how you find the next x after you already have a given x. So you have your x0 and your x1, or you just have your x0. So our x0 is going to be our initial condition. This is a given condition, and then we calculate the value of the function based off of that. So our n in that case would be time 0 plus 1. Now that's our time 1, and we base that off of our previous x. So we would plug in our x0 into these points here, and then we would find the value for x1. So on the horizontal axis are the parameter values R, and then on the vertical axis, we're finding where the function tends to settle to with almost all of the initial conditions, and that's what makes these things an attractor. This is just, so we're plugging in a bunch of different x0s. We're not just taking the same x0 and then iterating the function over and over again. We're taking different x0s, and then we get these vertical slices here. So I just wanted to explain that really quickly before I moved on, because I realized while I was editing that it wasn't all that clear. So now we're going to move on to chaos because we've been talking a lot about it and we haven't really defined it. The most I've said about chaos is you can think of it as local randomness and global determinism. This picture here is called the Lorentz attractor. This was my introduction to chaos, and it's what really got me excited about it because it just looks so freaking cool. So this is a system that I'm not going to explain, but I probably will in another video because it's really simple. Honestly, it looks kind of complicated, but it's a really simple system. But the way this looks only happens for one parameter value or a few parameter values in the system, after which it shows the same thing as the logistic map where, there's a period of chaos, and this attractor here shows the period of chaos. And then for other values of that parameter, this kind of thing looks different. Maybe there's only 1 point here, maybe it looks slightly different, but this is characteristic of the chaos of that particular system. So I'm basically going to make concrete the relation between fractals and chaos and hopefully just clear everything up. So chaos and fractals are two sides of the same coin. Chaos is the dynamical side, so what happens in time as a chaotic system evolves, and fractals are the static side, so the set of points the system evolves on. And I'll bring up the chaos game that I think I went through in part 2 of this series, where you pick some points at random based on this system of 3 vertices, and eventually all of these points settled into the Sierpinski triangle. So the Sierpinski triangle is the static side, the set of points the system evolves on. And then chaos is just what happens in time as the chaotic system evolves. So behavior in chaotic systems is aperiodic, meaning that no variable describing the state of the system undergoes a regular repetition of values. And this is kind of what makes chaos chaos, is that there's no conceivable pattern when you look at the values that it takes. It's kind of random, but at the same time, when you zoom out, it's got this structure. So we actually have a special name for attractors that are fractals, and we call them strange attractors. This is often the case when the dynamics on the attractor are chaotic, but strange non-chaotic attractors also exist. But the majority of the examples that you would see if you're looking into this or encountering these concepts for the first time, the strange attractors are the attractors of chaotic systems, just like the chaos game. And I messed up the slides here, I'm not going to fix that. If a strange attractor is chaotic, which means it's sensitive to initial conditions, which means, if you have 2 separate initial values for your x0, remember the logistic map, if you have 2 separate values for your x0 that are just a tiny bit different, they're like 1/1000th of a value different, the entire system, the value that the system takes as it evolves in time is going to be completely different for those 2 initial conditions. That exactly describes what's happening in chaos. So if a strange attractor is chaotic, which means it's sensitive to initial conditions, then any 2 arbitrarily close alternative initial points on the attractor after any of various numbers of iterations of the function or the system that describes the chaotic system will lead to points that are arbitrarily far apart, which is subject to the confines of the attractor, which means global determinism. So as the system evolves, the initial points will lead to points that are arbitrarily far apart, but at the same time, you're not going to have, these points aren't going to end up off of the attractor. So here's the Lorentz attractor over here again. And so if you start somewhere here and then you have another point here, it's not going to evolve fucking over here. It's going to stay on the attractor. It's just that when you start with these two initial conditions that are just ever so slightly different from each other, they're going to diverge rapidly. So thus a dynamic system with a chaotic attractor is locally unstable / random, yet globally stable / deterministic. Entropy in a chaotic system is high but never reaches equilibrium, aka it never reaches max entropy. So any small uncertainty that may exist in the initial conditions will grow exponentially with time. Eventually, uncertainty will become so large that we lose all useful knowledge of the state of the system. Even if we know the state of the system very precisely now, we can't predict the future trajectory forever. We can do it for a little while, but the error grows exponentially. This is essentially how I would summarize chaos, especially, again, emphasizing that locally random, globally deterministic property, which is going to be important when we think about markets. So hopefully there's a point in time where I can explore or explain the Lorentz system more in depth, because it's so cool because it's so easy to understand. But yeah, I don't really have time for that. So now we're just going to go on to the main point of this entire series. We're going to talk about fractal time, and I actually only have a few things to say about this before we actually get into the market analysis part, which will be sometime in the future. I still have to write the slides up for it, but so yeah, no, let's introduce fractal time. So previously in part 1, we said that the book aims to present tools for analyzing markets within a new fractal market hypothesis framework. So we haven't defined what that framework is. We're just going to say that we are going to say that markets can be modeled as fractal time series. And then we want to analyze them based on the fact that we're modeling them as fractal time series, because there's already tools to analyze fractal time series separately from markets, like the idea evolved separately. So we're just going to apply those tools to markets. This is in complete opposition to standard market technical analysis, which does not treat markets as having chaotic or fractal properties. Instead, markets are modeled by random, independent processes with Gaussian statistics, e.g., example, processes following a normal distribution. So Gaussian statistics is the same as stochastic, is the same as random, basically. We use fractal statistics rather than Gaussian stochastic statistics in fractal time series analysis to assess fractal characteristics of data, such as self-similarity, chaos, local randomness, global determinism, fractal dimension, etc. And again, fractal dimension is going to be pretty important when we analyze fractal time series, because again, fractal dimension is that one way that we can quantify fractals in a sense. Fractals in time inherently lack well-defined spatial characteristics, so we have to use different methodology to analyze them. So now we're going to talk about what exactly is a time series. Really simple, a time series is a sequence taken at successive, equally spaced points in time. Thus, it is a sequence of discrete time data. So on your horizontal axis, you'll have time, and you'll have equal steps in time that you sort of sample your data. And then on the vertical axis, you have whatever you're using to measure your data. So these are charts for the time series for the Mandelbrot set taken at fixed parameter values. So you fix the parameter of your Mandelbrot set. There's a relation that defines the Mandelbrot set that I haven't gone over. But this is kind of cool because we can tie it into chaos. So when we were talking about the logistic map, we were talking about how at certain values for the growth rate parameter R, we saw chaos, and at other values we saw, starvation, because it models population growth. So it's a similar thing with the Mandelbrot set. In the equation that defines the Mandelbrot set, we have for C value of negative 1.1, it's very patterned. This isn't chaotic at all. It's got a clear pattern. Same here for C equals negative 1.3, and then we're decreasing it by a small increment, and we still have a pattern. And then for some reason at c equals negative 1.9, we get chaos. So there's not really a discernible pattern here. But this is a time series that also shows chaos. And for c equals negative 1.9 on the Mandelbrot set, that's when we're going to see that fractal that I showed at the beginning, the one that we zoom in on, the characteristic fractal that we think of when we think of fractals. So now I'll just describe statistical self-similarity. For reference, this is the Koch curve, so the one that looks like a snowflake, the one that we use to talk about box or fractal dimension and box counting. This is the same thing, except that the orientation of the lines have been randomized. So it doesn't look like a fractal, but it has, but it is a statistical fractal. So the statistics on it have this kind of fractal self-similarity property. All right, so statistical self-similarity. Time series traces can only exhibit self-affinity since the orthogonal dimensions of such a trace have different units. This is why we can't say that time series are exactly self-similar. We can't even say that they're statistically self-similar. We say that they're statistically self-affine. So in self-affinity, scaling is not necessarily identical in all directions. But yeah, so we don't have to worry about this too much in order to understand statistical self-similarity or statistical self-affinity. We just basically have to understand that the fractal properties are statistical. They're not spatial. So you won't be able to really look at them, to really look at a fractal time series and be able to say, oh yeah, that's definitely a fractal. You have to analyze it with statistics. Exact and statistical self-affinity refer to structures whose precise details or statistical properties, respectively, are repeated as its two orthogonal dimensions are resized by independent quantities. A good example of statistically self-similar objects are random fractals, which I mentioned earlier. They use stochastic rules, and then these are just some examples that you can look up yourself, and we talked about trajectories of Brownian motion. And to kind of make this idea clearer, because this part is kind of confusing, where we're saying they can only exhibit self-affinity since the orthogonal dimensions of time series traces have different units. This is kind of what we're talking about. So this would be like our original time series trace. So we have trading days, so 500 days, 1,000 days, 1,500 days, so on. And then we have our price. So this is our measure. This is our measurement on the vertical axis here. So this is our original trace here in the blue. And then when we look at a portion of this trace up here, we can see that we've zoomed in now. So between 1,500 and 2,500 is right here. So this is, but at the same time, the scale, the dimensions on the vertical axis is the same as below. So the horizontal axis scaled differently. It's more zoomed in, but the vertical axis is the same. See, we have 20, 40, 60, 80, 100, and we still have 20, 40, 60, 80, 100. It's just, so the axes, the orthogonal components that we're using to trace this time series, they've scaled differently. So in a regular fractal, the units on both of these axes would have been the same. And that's why we can't say that they're self-similar. We just call this property self-affine. It's just a way to categorize it. So now that we've talked about what a time series is and a little bit about what a fractal time series is, now we'll kind of make more concrete what a fractal time series is. So this is an example of a fractal time series, actually. And as you can see, you can't really tell that it is a fractal, but when you analyze it with statistical methods, you will find that. And I won't go over that in in this video, but I will start to go over that in the next couple of videos that I do, which I haven't created the slides for, as I've said. So fractal time series are statistically self-affine, as we've just mentioned. Fractal time series are those time series which are chaotic, so they're sensitive to initial conditions, they're nonlinear, which means their equations of motion have a higher power than 1. I just put that in there because I learned about equations of motions last semester. It doesn't really matter. So we kind of know all of the properties of fractals already, and that's just, we're just applying that. We're just going to apply those same properties of fractals to a time series, and we're just going to measure those properties a different way. So the fractal dimension of a time series shows how turbulent the time series is, and also measures the degree to which the time series is scale invariant. So it quantifies how self-similar the time series is, and how well the time series is described by a power law. Fractal dimension of a time series cannot be quantified using box counting or other spatial methods. Since the two axes of a plot representing a time series dataset generally represent variables with distinct units, the geometric aspect ratio of such a plot is fundamentally undefined, whereas a spatial entity has orthogonal dimensions with the same units. So this is what I explained in the last slide, where I showed that the horizontal axis scaled differently from the vertical axis when you zoomed in. So again, we're looking at that zooming, that scaling property of the time series. It's just that with regular fractals, the two axes scale the same way, and with time series, one of the axes is going to scale differently than the other. So it scales statistically in time. So again, the spatial properties, like when you look at the graph is not going to scale like a fractal. The statistical properties of that time series will scale like a fractal, because a fractal isn't really a graph. It's like a visual depiction, like, you know, the Koch curve, the rough kind of snowflake looking thing. Kind of looks like a graph, but it's not a graph. It's completely different. So a time series is more of a graph. So the point of all this is that the statistics of a time series with fractal dimensions different from a random walk, so 1.50, we discussed this, would be very different from Gaussian statistics and would not necessarily be contained within the normal distribution, which is how we normally model market statistics. So if we do have, if we can describe a market return time series as a fractal, if we can say that it has fractal statistics, then necessarily it's not going to follow a normal distribution. And so, you know, all of our standard methods for, you know, determining risk and determining expected return, we can basically just throw it out the window, because this is a better model. I think it will be a better model anyways. Markets are somewhere between deterministic and random. So we know that the fractal dimension of any market time series is going to be between 1 dimensions and 1.50 dimensions. It's going to be, somewhere in there. And again, we see that kind of fractal or chaos characteristic. It's somewhere between deterministic and random, which is kind of how you can describe a chaotic system: locally random, globally deterministic. Finally, the normal distribution describes the probability of certain market moves. So steps, aka the step size in Brownian motion in a random walk, from a given initial position in a random walk Brownian motion scenario. So the normal distribution describes the probability of certain market moves in our standard model. So if we have a different statistical distribution, we're going to have different probabilities of certain market moves, and we'll be able to find patterns and hopefully analyze it so that investors can get more certain returns, or understand their investments in a different way. So yeah, that's all I have for this part of the series. I will get working on the next part, which is where we get into actually analyzing markets right away. But yeah, hopefully you learned something. Hopefully I explained myself well. Hopefully you enjoyed it. And if you have any questions, just leave them in the comments. I'll do my best to answer it. I hope I didn't make any mistakes, but I probably did. So yeah, just let me know. And thanks for watching. I'll see you... God, what is this, part 5 now? This is part 4 or 5, so I'll see you in the next part after. Bye.